Hi there, Mr. Sutton here, bringing you the AB Calculus 5.9 classwork solutions on FTC graphical analysis. For this problem, we're given the graph of f and told we have horizontal tangents at x equals 2 and 5, may or may not be important, and then g is this integral of f function here. We want to know at what values of x the g function has points of inflection. So if I'm asking about points of inflection with g, one way to figure this out is to figure out where g prime is going from increasing to decreasing, because that's really telling us where g double prime is going from positive to negative, or from decreasing to increasing, g double prime going from negative to positive. So let's just start off by connecting the g function and the f graph here. If we differentiate both sides of this equation using our fundamental theorem, we see that g prime is really just f of x. And f of x, this graph here, is going from increasing to decreasing at x equals 2, and it's going from decreasing to increasing, another change in direction, at x equals 5. Based off of this alone, we can conclude that g has points of inflection at x equals 2 and 5, which gives us answer choice C. For this graph, we have the graph of some differentiable function f shown here, and we're told that some h function is just the integral of this graph from 0 to x. And based off of that, we want to know what's true here. So we're basically asked to compare the values of h prime, and h double prime at the x value 6. So let's just go through each of these and see what we can figure out. So if we're asking for h of 6, we're essentially asking for the integral from 0 to 6 of our f graph, which is to say we're asking for the area under the curve as we go from 0 to 6. Now, we don't really know what f is doing in terms of an actual algebraic function, so we can't figure out exactly how much area is. We could sort of estimate it by using rectangles, but at the very least we can conclude, since we're going from left to right on area that's below the x-axis, this is all negative area. So this is going to be a negative value. All right, well, hopefully that's enough. Let's keep going and figure out h prime of 6. So since h is just the integral of f here, using our fundamental theorem and just plugging in x for t, we can see that h prime equals just f of x. So that means that h prime of 6 just equals f of 6, which is to say the value of the y value on this f graph here. So at the x value 6, our y value is just 0. We can tell that for certain. Well, we know that 0 is bigger than anything less than 0, so that at least allows us to compare these two values. Let's check out h double prime now. H double prime of 6 is just going to be f prime of 6. It's just going to be the slope of our f graph at the x value 6. And again, we don't know exactly what this slope is, but we can at least tell that it's positive. We're going up and to the right. So comparing these now, we have a negative, 0, and a positive. Well, the negative, h of 6, has to be the smallest of those, and then the 0 value, h prime of 6, is going to be next, followed by the positive number, h double prime of 6. Carefully choosing that from the answer choices, that actually ends up being the first one, choice A. For this problem, we're given the graph of f prime up here, and told that f of 0 equals 0. Based off of this, we want to figure out which of the following could be the graph of f here. Now, the low-hanging fruit is to say, okay, we've got the point 0, 0 on the original graph. Do any of these not have the point 0, 0? And the answer, if you look at all of these, is no. These all go through the origin, so we actually have to do some calculus. All right, f prime, right here. Well, we know that wherever f prime changes from positive to negative or negative to positive, we're going to have smooth turnarounds if those are just x crossings. So taking a look at our graphs, where do we have smooth turnarounds at 2 and 3? So choice A, it kind of looks like we have them at 2 and 3. We also have another one here at 0.5, though, so we could probably eliminate A based off of that. B also has an extra smooth turnaround that we were not expecting at 1, so that could be eliminated. And E also has an extra smooth turnaround at 1, so we could really narrow it down to C or D based off of this. Now, another way you could have done this is you can note that f prime is going to be positive between 0 and 2 and 3 and 4 if you look at this f prime graph, which means the graph of f itself must be increasing on the intervals from 0 to 2 and 3 to 4. And looking at all these graphs, the only one that's increasing from 0 to 2 and 3 to 4 are C and D. So multiple ways to narrow it down to C and D. All right, next up, Really all that's left to look at is concavity at this point. So we see that f prime, this graph here, is increasing from 0 to 1 and also from 2.5 to 3.5, just at those spots. What that means is that the graph of f itself is concave up on those intervals. So looking at choices C and D, C appears to be concave up between 0 and 1 and also from 2.5 to 3.5. D, well, from 0 to 1, D is actually concave down. So we can eliminate D, and that just leaves us with choice C. For this problem, f is the function with a first derivative defined as f prime equals sine of x cubed from 0 to 2. We want to know what value of x f attains its maximum value on the interval from 0 to 2. So this one's a little bit tricky because, for one thing, they didn't actually give you any values of the f function. They gave you the derivative, but we don't actually know what f equals at any particular x value. So what we're going to do here is a little bit of derivative analysis. I'm going to graph this out on my grapher between 0 and 2, and I'm at least going to see where it crosses the x-axis. That's going to give me some critical values. I'm also going to have to test out, using my candidates test, the endpoints of 0 and 2, because we're looking for basically an absolute max on a closed interval. So let's put this in the calculator. So here we are. I've got sine of x cubed in my y1, and again, this is the derivative of the function that I'm trying to maximize. So let me go to window now, and I'm going to set my x values between 0 and 2, and then do zoom fit, zoom 0. So that'll give me the perfect window on what my function is doing between 0 and 2. And we see that there's some crossings here. We're crossing the x-axis right here and right here. However, we actually don't need to test all of these if we're looking for a max. We only need to test the spots where we're crossing from positive to negative, because that would give us a local max. Over here, we're going negative to positive. If something's a local min, if something's the lowest value in its area, it's not going to be the max for the function. So let's just do, let's see here, we'll do second and trace and do 0. And we're just going to calculate this 0 right here. So let me just move my spider a little bit closer and a little bit to the right and press enter again. Press enter a third time. And then we see about 1.4645 or 465 if we round it off. So I see that f prime changes from positive to negative only at 1.4646. All right. So before I go ahead and conclude that this is the location of my absolute max, which it probably is, because we've had all this positive area, a bunch of negative area, and only a little bit more positive area. If I was in a rush, I would say this is the absolute max, but if you have time, we can actually test these numbers out. So I don't know what the f function is, because again, I don't have a value for f of anything, but I can talk about, I'm going to call this the g function right here. Let's let g of b be the integral from 0 to b of f prime. Basically, g is giving us the total change in f from 0 to some interval. So I'm just going to basically plug the endpoints 0 and 2 and also this 1.5 or 465 critical value into my g function, and whatever gives us the biggest number, that's going to be the biggest change in f, so that would tell us where the maximum value of f has to be. So let me plug this in the calculator. To do that, I'm going to go back to my y equals, down to y2, and now I'm going to get an integral, so I'm going to do math 9 to pull up my integral here. I've got an integral from 0 to, and now I need an input value here. Usually you shouldn't make this x up here and also use x's down here in your formula, but your calculator can actually figure it out if you do that, even though it's not proper notation on paper. So I'm going to put an x up here, and down here, what am I integrating? Well, I'm integrating this sine function here. I'm just going to save myself some time and do alpha trace and pull up the y1 from my y equals menu, and then I'm going to do dx. Again, this letter should not match if you're doing this on paper, but for some reason your calculator has no trouble figuring out what you really mean. All right, quitting out of there, let's test some things out now. The first thing I'm going to test out is g of 0. Now, I actually don't even need the calculator to do this, because if I'm integrating from 0 to 0, that's an empty integral, which should give us 0. But let's just plug it in the calculator anyway. to make sure our function works. So I'm doing alpha trace to pull up y2 now, plugging 0 in there, and it comes out to 0 like we expected. The next value I'll test out is g of 1.4646. So let me just yank that input from before, and 1.4646. And if I were really clever, I would have saved the value from my graph, that 0, as a constant and used it. But this doesn't take too much more time. So we get about 0.591. And then I'm also going to test out g of 2. I have to test the other endpoint. It's probably not going to be the winner because we had all this negative area coming before a little bit of positive area. But it's not going to hurt to test it out since we've already got this function in our calculator. And that comes out to about 0.452. Okay. So out of all of these, the biggest change in the f function is occurring then at this critical value. So that means that we have to go with choice C. We have the f max value has to be this at this x value here. Now it's worth noting that this value is not the actual value of f necessarily. This is just the change from 0 to this spot. For this problem, we're given the derivative of f up here. They were sneaky and spelled it out instead of writing f prime. So we have to figure out the graph of f from these answer choices. A quick way to do this is to look at your critical values for f prime up here. I guess they actually did label it in the graph. So we've got -1 and 1 as x-intercepts. That means the graph of f is going to have smooth turnarounds, local max or mins, at those values. Looking at our answer choices, only B and C have smooth turnarounds at those values, so we have to dig a little bit deeper. Another way I approached this is I said that f prime was positive from -infinity to -1 and 1 to infinity, and so that means that the f function's got to be increasing on those intervals, and I noted that f prime was negative between -1 and 1, so f is decreasing between -1 and 1. Looking at our answer choices B and C, the only one where we're increasing before and after the ones is going to be choice B. So that's our answer. For this problem, f prime is given as the absolute value of x minus 2. Based off of that, we want to know which of these could be the f function. So it helps if you understand what this absolute value of x minus 2 actually looks like on a graph. It actually looks exactly like choice A. So if you realize this, they were actually very nice and essentially gave you a picture of f prime in choice A. If you didn't realize this, then this was a much tougher problem because this was a no calculator problem. All right, so where do we go from here? Well, looking at the graph of f prime, we have an x-intercept at 2, but we don't have a sign change, so it's not necessarily a smooth turnaround. Maybe some kind of plateau, who really knows? We do notice that the sign of f prime is positive. It's greater than or equal to 0 for like everywhere because it's absolute value. So since we're greater than or equal to 0 for all x values, that means that f itself, well, we can't say that it's increasing everywhere, but it's at least non-decreasing. It never goes down. At best, it just kind of breaks even and then goes up again. So taking a look at our answer choices, I mean, A we've already, I guess we could take a look at A, but you'll notice that A is decreasing in spots, so A already is not going to be the answer choice. B also decreasing right here. C is decreasing. D is not decreasing anywhere. D is continuously increasing. We do have this weird jump, but we are increasing before and after that. And then we have choice E, where we're increasing everywhere. So between D and E, we need a little more information to choose between these. Another key feature the graph of f prime has is that it's continuous. Now the reason this is important is because that means that f itself is differentiable and therefore also continuous. So that means we're looking for a continuous graph which rules out choice D. So it's got to be choice E then. For this one, we're told that f prime is positive and f double prime is negative for all x values, and we want to pick the table that best represents the f function here, or some f function based off these conditions. So just translating these conditions, f prime being positive means that the f function is increasing, and f double prime being less than 0, negative, means that the f function is concave down. Well, if we are increasing concave down, just kind of drawing out what that looks like, that's like the left side of a frowny face. So basically, we're increasing, but we're slowing down. We're going at a decreasing rate. Another way you can think about this is if you could think of f prime as your velocity and f double prime as your acceleration. If velocity and acceleration are working against each other, you're slowing down. But we are increasing at least. So let's go through the answer choices and see what each of these is doing. Choice A, it looks like we are decreasing on that one. We're going from 4 to 3 to 1. So that's a pretty poor answer choice because we're not increasing. Choice B is just staying constant. C is increasing but at a constant rate. D is increasing at an increasing rate. We're going from 1 to 2 for the difference. And then we're going, let's see, E is going up but at a decreasing rate. We changed 2 and then change 1. So increasing at a decreasing rate, that's choice E. For the next few problems, we're going to be using this diagram and this g function, which equals the integral of the f function that's graphed up here. So for part A, they want us to find g of 4 and g of negative 2. So essentially, you just have to plug 4 and negative 2 into the upper limit of this integral and figure out what that comes out to. So we've got g of 4. That's the integral from 1 to 4 of the f function. Now, when we integrate the f function up here, we're essentially just finding the area under it. So if I'm going from 1 to 4, there's a few different areas that I need to take into account. One of them is the trapezoid between 1 and 2. So to get the area of that trapezoid, I need to do a base of 4 plus a base of 1 over 2 times a height of 1. So that's just using our trapezoid formula, base 1 plus base 2 over 2 times height. And now we have a triangle from 2 to 3. That's going to be 1/2 times a base of 1 times a height of 1. And these are both positive areas because we're moving to the right and we're above the x-axis. But now below the x-axis and moving to the right, well, that's going to be a negative area. So this is going to be minus 1/2 times 1 times 1. And there's no need to simplify this, but if we wanted to, we see that these terms here, these triangles, are essentially canceling each other out. So it's really just the area of this trapezoid which gets counted, and that's going to be 5 over 2. Moving on to g of negative 2, now we're going from 1 to negative 2 area under f, and since we're moving backwards now to the left, all the area that used to be positive is now going to be considered negative, and vice versa. So we've really just got one shape here, this big triangle from negative 2 to 1. So we have a height, we have a base of 3 and a height of 4, but now since we're going backwards above the x-axis, we're going to be doing negative 1/2 times 3 times 4. So let's see, negative half of 4 is negative 2 times 3 gives us a simplified total of negative 6. For part B on this question, we're asked to find the instantaneous rate of change of g with respect to x at x equals 1. So this is just code for finding g prime of 1. Now the key on this is realizing based off of this formula here, if we use our first fundamental theorem of calculus, we've got essentially g prime equals f of x. So that means that g prime of 1 equals f of 1. And f of 1, that's just the y value when x equals 1 on the f function here. That's going to be up here at 4. And they are actually nice and just spelled out that this was 1 comma 4. For this problem, we're trying to find the absolute minimum value of g on the interval negative 2 to 4 and justify it. So for this one, since we've got a closed interval and we're looking for an absolute min or max, we use the candidates test, which means we have to consider the endpoints and also certain critical values in between. Now I say certain critical values because if you word your justification correctly, the only critical values you really care about are the local mins. Because if something's not at least the smallest value in its immediate area, there's no way it's going to be the smallest value for the entire graph. So let's take a look at critical values. So g prime, we said that's really just f of x. And f of x, the graph here, does not change from negative to positive, which would give us at least a local min anywhere on here. We have this one critical value where we're changing from positive to negative, but this is going to yield a local max. So we don't actually have to consider it as long as we talk about that here. So the way I'm wording this, f of x or g prime does not change negative to positive on -2 to 4, the open interval from -2 to 4. So therefore, we're only going to consider the endpoints. Now, this is good news because we actually already know the value of g of -2 and g of 4. So from part A, we already found that g of -2 was -6. That was when you went backwards and found the area of this triangle here. But you were going backwards, so it was negative. And then g of 4, you might remember, was 5/2. That was the trapezoid and the two triangles there. So just looking at these two, we see that -6 is the absolute minimum for this graph. For the last part here, we have the second derivative of g is not defined at x equals 1 and x equals 2, which makes sense because if you're taking the derivative essentially of this f function here, you've got corners at these spots, so it's not differentiable there. So how many of these values are x-coordinates of points of inflection of the graph of g? Justify your answer. So the easiest way to find a point of inflection, if you already have the derivative of a graph, which we do here, because remember, g prime of x is really just f of x, this graph here. Easiest way to work with g prime is just to see where it goes from increasing to decreasing or decreasing to increasing. Those are both going to be counted as points of inflection. So looking up here, we see that our first derivative, g of x, or f, is going from increasing to decreasing at x equals 1. So therefore, we have a point of inflection at x equals 1 for g, and that's all the justification we need here, increasing to decreasing. Looking at x equals 2, this is going from decreasing to still decreasing. So g prime does not change direction at x equals 2. So therefore, there is no point of inflection at x equals 2. So how many of these are points of inflection? Well, just x equals 1.